Okay, so now we're going to take a look at an example of how to evaluate a definite integral. And remember the difference between an indefinite and a definite integral. A definite integral has these bounds, or what we call the limits of integration. So in this integral, we're trying to evaluate 0 to ln 4. Okay? Now, what you'll notice is that I wrote the exact same integral up twice. And the reason I did that was because I want to show you two different methodologies to be able to evaluate. Okay? The first way, the way that I like better, is using a dummy variable. And the reason I like the dummy variable is because when you get to higher level mathematics, you're not always going to have numbers as the limits of integration. You're going to have variables. Sometimes you're going to have more than one variable. You're going to have a plane. So I want to ensure that when you guys do this, that you know both techniques. Now, when you're just starting calculus, integral calculus, maybe the second way that we do it, when we do a change of variable, might be better. Okay? So let's go ahead and try to evaluate this guy. All right. Now, one of the things that you'll notice is that this is almost basic. The reason it's not basic is because we have an x over 3, not just an x. If it was just an x, we'd be in good shape. We could do this problem a lot easier. So let's do a number of things. Okay? I'm going to go ahead and suggest that let's make the exponent x over 3 equal to our u. Okay? Let's try a u substitution. So let's let u be equal to x over 3. Our derivative, du, the derivative of x is 1, so we end up with a 1 over 3 dx. Now, unfortunately, in our problem, we have a 2. All right, so we're not going to be able to use the 1/3 in tandem with the 2. So let's do this. Let's multiply both sides of our derivative by 3, and that'll just give us the dx. So at least we can substitute for the variables and the differential operator. Then we can worry about the numerical factors. Okay, so I'm going to multiply both sides by 3. So I get 3 du is going to be equal to dx. Notice that we're not in terms of u any longer. Because we're not in terms of u, we can't use, or I'm sorry, we're not in terms of x any longer, excuse me. So now what we have to do is we have to get rid of the 0 to ln 4. Okay? So here's what we're going to do with this. My integral now becomes the integral, instead of 0 to ln 4, I'm going to say from a to b. And that's why I said before, dummy variables. We just use these two variables to represent two variables that are somewhat, or some bounds in terms of u. We're not quite sure what they are. The 2 gets dropped down. X over 3 becomes u. And then instead of dx, we said that 3 du is going to be dx. So I'm going to say times 3 du. Okay. Now, before we perform any integration, let's factor out the 2 and the 3 to get down to a basic integral. We know that 2 times 3 is 6, so let's factor a 6 out. So we get 6 integrals from a to b of e to the u du. Now, we know that this is a basic integral. We know the antiderivative of e to the u is e to the u. Surprise. So we're going to say 6e to the u from a to b. Okay, those are our dummy variables. Notice we don't have a plus c because it's a definite integral. The only time you use the plus c is when we're dealing with indefinite integrals. Now what I'm going to do is I'm going to back substitute for u, and I'm also going to back substitute for b and a. Okay. So I'm going to say that now we're going to get 6e to the x over 3. And then instead of going from a to b, it's going to range from 0 to ln 4. So if I substitute now using our fundamental theorem of calculus, remember it's f at b minus f at a. Okay, so this is going to become 6e to the, let's just say 1/3 natural log of 4. So again, all I did was I basically factored the 1/3 in front, substituted ln 4 back in for x, minus 6 natural logs, or I'm sorry, 6e to the 1/3 times 0. Okay, again, that's just using our fundamental theorem of calculus. Now, we can simplify this answer. Okay? In fact, if you wanted to get the back of the book answer, the one that's more traditional, you'd want to go ahead and use some algebra with this. Okay? Stuff that you probably looked at in pre-calculus. A lot of you guys probably have an inclination that this natural log and this e are going to do something nice to simplify, and in fact they are. Okay? Remember that e and ln are inverses of one another. Okay? They're inverse bases, if you would. All we have to do is kind of get this 1/3 away from the 4. Okay? So let's go ahead and let's rewrite this now as 6e, and if you recall, if you have a coefficient in front of a logarithm, you can make it into the exponent. So this now becomes 6e to the natural log of 4 to the 1/3 power minus 6e, 1/3 times 0 is 0. Okay? Now we're starting to get this cleaned up a lot. All right. So, like we said, e and ln are inverses of one another. Okay? So these guys are actually going to take care of one another, and the 4 to the 1/3 is all that's going to be left over. Okay? So I'm going to wind up, let's go over here. E and ln go away, so I'm left with 6 times 4 to the 1/3. And then we have 6e to the 0. A common error that I see a lot of my students make is that they think anything with a 0 goes away. Remember from your basic algebra, anything to the 0 power is 1, okay? Except if it's 0 to the 0. So we get 6 times 1. And then if I wanted to clean this up even further, another way that I could write the answer is I could say that this becomes 6 cube roots of 4. Remember, if you have a rational exponent, the denominator is the index, the numerator is the exponent under the radical, and by multivariable calculus implementations, 6 times 1 is 6. Another way that you guys might see this written is that the 6 is factored. Okay, so one other way that you can write it is 6 times the quantity of the cube root of 4 minus 1. Usually, this is going to be the back of the book answer, okay? Because most of the time, whenever you look in your textbook, they want you to factor anything, okay? So that way, if there's any operations inside, you can do them discretely. So this is the dummy variable method, okay? And again, all we did was we used our U-Substitution, and then once we got down to the U-Substitution, then we just plugged in the a and the b after the integration. Now, let's see the second way of trying to evaluate this. Let's use the change of variable method, where we retain the original limits of integration. Okay? So, we already know the technique for this. We already know that u is x over 3. We know that du is 1/3 dx. And we know that 3 du is dx. Okay? That's just like what we did in the previous problem. Now, here's what's different about this problem and the previous problem. What we're going to do is we're going to take the limits of integration, the 0 and the ln 4, and we're going to plug them in right here. Okay? Because u is equal to x over 3. So, we're going to say, let's just do it over here. If x equals 0, we could say that u is equal to 0 over 3. And again, that's from right here. Okay? We know that 0 over 3 is equal to 0. let's say now that we have u is equal to natural log of 4. So if u is equal to the natural log of 4, then we could just plug ln 4 back in up here. So we could say u is going to be equal to natural log of 4 over 3. Or, just like we saw before, remember the algebra that we did before? Where we put the 1/3 and we moved it as the exponent. We could do that. So we can say this becomes ln of 4 to the 1/3. Or, just like we also said before, this could become the natural log of the 3rd root of 4. So the algebra that we're doing is the same. We're still moving the coefficient to the rational exponent, then we're changing the rational exponent into a radical expression. We're basically just doing what we did towards the end of the problem at the beginning of the problem. All right. So, notice what happens now. We have an upper bound for u. We have a lower bound for u. We have all the x's in terms of u. So, might as well just go ahead and substitute. Okay? So, here's our substitution. Our integral becomes 2e to the u, not x over 3. So 2e to the u. Instead of dx, we're going to call that 3 du. And we're not using the dummy variable anymore. We're going to go ahead and say that the lower limit, when x is 0, u is 0. We're going to say that instead of ln 4, we get ln 3rd root of 4. So really, the only difference is that now, instead of a to b, now we have 0 to ln 4, ln cube root of 4, excuse me. Let's factor the 6 out just like we did in the previous problem. So now I have 6 integrals from 0 to ln cube root of 4 e to the u du. And now we can see that we have the exact same integral that we had right here, except that instead of a to b, now we have the limits 0 to ln cube root of 4. Antiderivative of e to the u is e to the u. So I have 6 e to the u from 0 to ln cube root of 4. I don't have to back substitute for x. The reason being is because it's a definite integral. We're just trying to find the value of that definite integral. We already know that these are the limits of the change of variable. So now we can substitute ln cube root of 4 and 0 back in for u. So let's go ahead and do that, use our fundamental theorem. We have 6e to the natural log cube root of 4 minus 6e to the 0. In the previous problem, we saw that e and ln are inverses. So what I'm left with now is just the cube root of 4. So I get 6 cube roots of 4. And we already know that e to the 0 is 1. So we get 6 times 1. Which is almost exactly what we have right here, except now we just have the cube root of 4 instead. Okay? So you guys can see that the answer is going to wind up being the same. We can factor the 6. So if I was to factor the 6 from this thing, I end up with 6 quantity cube root of 4 minus 1. So I was either really lucky or the methodology actually works. So this is 2 different ways to do it. Going forth, whenever we do these types of problems, what I'll generally do is I'll use the first method. And that'll help you guys that are going on to Calc 3, differential equations, etc., that have to change to multivariable sorts of integrals.